Welcome back, everybody. Today we're going to be taking a look at complex eigenvalue problems. We looked at the real eigenvalue case on Monday, introduced the eigenvalue method, and got used to that. What I'd like to do at the start of each of these videos is go over some of the stuff that I've added to Canvas just to make sure you're keeping up with the material. My most recent announcement in Canvas was a listing of all of the lecture videos and content for March 23rd through March 27th, this current week. You can see here I have the video lecture from Monday, along with the notes from that lecture, telling you what sections to read. This video is over section 3.4, so it'll be up momentarily after I finish recording. And then we'll have another video on Friday for section 3.5. The assignments due this week are quiz 6, which is up as of the time of this video. So you have access to quiz 6 now. The practice quiz has been up for a little bit already. The Maple quiz is due this Friday, and you should be thinking about and working on project 2, although it's not due for a couple more weeks now. But that's kind of what's going on this week. We are in section 3.1 through 3.5 dealing with the eigenvalue method. And you can see I've been hosting the videos from each week here as well, along with Maple files that you should use, class notes, things like that. All right, if we want to jump into this, our topic for today is dealing with specifically an introduction to complex variables, and then we're going to talk about complex eigenvalues. Now, this is actually one of the more important topics for you to learn from this course, is not only to be exposed to complex variables and complex eigenvalues, but to be able to manipulate them to solve problems like this. You'll see it in a host of other physics and engineering classes, and this is kind of your first taste of it if you haven't already run into it in like a circuits class or classical mechanics or something like that. So I'm going to start with just some of the basics. We know that the imaginary number I is equal to the square root of -1. One of the really interesting ways to remember this is to think of the complex plane. And so this is the real axis of the complex plane. This is the imaginary axis. So this is where I would be. And if you square I, you get -1, which is right down here. So if this is I squared. And if you cube I, you get -I, which is I cubed, which is there. And then over here, if you take I to the 4th, you get 1. What I like students to remember is if you multiply by I, what happens, right? So if you have I, multiply by I again, you get -1. If you multiply I cubed, you go I, then I, so you get down to -I. If you multiply I by itself 4 times, you get back to 1, and so on. So you create kind of this circle. It's called the circle of unity. We may talk about that in a later class, but you create this circle of different values of I in the complex plane. And so, you know, the long and short of this is I is, when raising it to a power, has period 4. Every 4 powers of I returns you to 1, which then the 5th power would return you back to I. So how are we going to use this? Well, I want to teach you some notation, some terminology associated with these. So in rectangular form, every complex number is a plus bi, where a is called the real part of the complex number z, and b is called the imaginary part of the complex number z. So I have a couple of examples here of complex numbers we're going to use throughout these examples. The reason that this is called the rectangular form is that if you were to plot these numbers on the complex plane, which has the real axis and the imaginary axis are things that are multiplied by I, then the number z1, 3 plus 2i, would be 3 and 2, so this would be the number 3 plus 2i, and you plot this rectangularly just like you would in the xy plane. Similarly, -1 and -5 would give you the point -1 minus 5i, which is z2. So this is called a rectangular form of a complex number. We're going to talk about another form of a complex number known as a polar form today, but this is what you are probably most familiar with already. So what is the complex conjugate of a complex number? Well, if z is a plus bi, then z bar, the complex conjugate, is a minus bi. So using the examples above, the complex conjugate of z1 is 3 minus 2i, and the complex conjugate of z2 is minus 1 plus 5i. Notice it's only the imaginary term that changes. So on z2, I don't also change the negative 1 to a positive 1. I just change the imaginary term to a positive. The interesting thing that comes out of this is if you take a complex conjugate, so z bar times z, which is a minus bi times a plus bi, this result is always real. So if you FOIL this out, you get a squared minus abi plus abi, and then you got minus b squared I squared. But remember, I squared is negative 1, so it's minus b squared negative 1, or a squared plus b squared. So a complex number times its conjugate is always a real value. We're going to talk more about that real value coming up very, very soon, but that's z bar times z. So how do we define the real part of a complex number and the imaginary part of a complex number? And this should say in terms of conjugates. Well, if you look, if z is a plus bi and z bar is a minus bi, then what do you get if you take z plus z bar? Well, z plus z bar would be 2a, which means that if I wanted to solve for the real part, which is a, that's the average of the complex number and its conjugate. So this is defined as the real part of the complex number z. Similarly, if you were to subtract a complex number and its conjugate, what you'll notice is the a's cancel. So subtracting these two, the a's cancel, and you've got b minus negative bi, so it would be 2bi. So if you want to solve this for b, you would divide by 2i. And that is the imaginary part of a complex number. So the average of the complex number and its conjugate is its real part, and this kind of half difference divided by I is the imaginary part. Okay, moving on. How do we multiply, divide, add, and subtract complex numbers? So let me bring down our two pieces here. We've got z1, which is 3 plus 2i, and we've got z2, which is minus 1 minus 5i. So let's just take these one at a time. I'll start with the simplest one first, which is addition, z1 plus z2. So if you were to add these two together, you've got 3 plus 2i plus negative 1 minus 5i. You can think of I as though it were like a variable. It's not. Remember, I is a number, but you can treat it as though it were an x, and you collect terms based on whether they have x or not. So you've got the constant terms, 3 and negative 1, and you have the I terms, which are 2 and negative 5, and now we've collected like terms. So 3, negative 1 give you 2, 2 minus 5 is negative 3, so we have added those two complex numbers. Okay, so similarly, if you were to subtract, it's the same thing. You're going to collect like terms. So this would be 3 minus a negative 1, and then it would be minus 2 plus 5i. So you would get 4 plus 3i if you were to subtract them. Okay. How about multiplication? So z1 times z2. Well, the way to handle this is simply to FOIL and then collect like terms. So let me see if I can move this over a little bit. So we're going to FOIL this the way you normally would. You'd get negative 3 minus 2i minus 15i minus 10i squared. So that's minus 17i. Keep in mind that the I squared here is negative 1, so that's negative 10 times negative 1 or positive 10. Negative 3 plus 10 is 7, so you get 7 minus 17i would be the multiplication of those two in rectangular form. Finally, the most interesting one is division. So division here, you're going to take 3 plus 2i and you're going to divide it by negative 1 minus 5i. It turns out that the best way to handle division is multiplying by the conjugate. So if you multiply by the conjugate of the denominator, that's negative 1 plus 5i divided by negative 1 plus 5i. And we'll FOIL across the top. So foiling across the top would give you negative 3, and then it would also give you a minus 10. So negative 3 minus 10 would be negative 13. And then the I terms would be minus 2 plus 15, which would be 13, I believe. So that's what the numerator would give you. And then watch how easy the denominator is. The denominator is z2 times its conjugate, right? You've got z2 times z2 bar. Well, from what we did just above, if you multiply a number by its conjugate, you get a squared plus b squared. So here, you would get a squared plus b squared. You'd get negative 1 squared plus negative 5 squared, which would be 1 plus 25 or 26. So dividing these two, you've got negative 13/26 plus 13/26 I, or if we reduced, minus 1/2 plus I over 2. So the best way to do the division of two complex numbers is by multiplying by the conjugate of the denominator. All right, so modulus is the next term that we need to talk about. What is the modulus of a complex number? So the modulus of the complex number z is defined as the square root of a squared plus b squared, which a squared plus b squared is a conjugate times itself, so you'll also see it written this way. Now, what is it though? Right? It's this quantity, but what is important about this quantity? In other words, what is the geometric significance of that quantity? Well, recall if we're doing this in rectangular form, so this is the real axis, this is the imaginary axis, so real, imaginary, and you're looking at the number a plus bi. So this would be a, the real part, the imaginary part is b, and if you were to look at this triangle that's formed, it is a right triangle where this length is a, this length is b, so we know by Pythagorean theorem this length is the square root of a squared plus b squared. So in other words, the modulus of a complex number is the length of the ray emanating from the origin that locates the point in the rectangular plane. So if this is the number z, then the modulus of z is the length of that ray, or the length of that vector, if you will. So we think of it as the magnitude or the size of the complex number. All right, polar form. And this is where things start to get interesting for us today. I want us to take that exact same picture. So that exact same picture we just dealt with, you've got a imaginary axis, you've got a real axis. So we're in the complex plane. We're looking at the number a plus bi. Once again, we know that this triangle is important. It will show up. We know that this side is a, this side is b. However, rather than try to locate points in the plane by doing it rectangularly, I could locate points in the plane by thinking of this vector as going out the modulus and then tilting up by whatever this angle is. So I'm going to introduce a couple of new variables. I'm going to introduce the variable angle, or the angle variable theta. And then I'm going to call the length of this, which we know is square root of a squared plus b squared, the modulus. I'm going to call that the variable r. So when you locate points in this way, like locating them on a radar, for instance, then you're using what are called polar coordinates. And so the change of variable for polar coordinates here is if you have a plus bi, or maybe x plus iy, depending on how you want to look at it, we know that b is r sine theta, and we know that a is r cosine theta. And so the modulus then is just r. What this tells us is a way to think about complex numbers slightly differently. For example, if I said that z is a plus bi and I wanted to convert this to r and theta, you can see that a is r cosine theta, b is r sine theta. If we factor out the r, which is the modulus, you've got cosine theta plus I sine theta. And it just so happens that this value here is a very special value in mathematics. We refer to it as e to the I theta. And this is called Euler's formula. Now, here's the interesting thing about this. There is no possible way that I can show you algebraically that this is equal to this. Right now I'm telling you that these two things are the same, and I'm going to give you some evidence here in a second to convince you of that fact. But there's not really an algebraic operation that says this is this. It's just Euler noticed that these two things behave. They have all the same properties. So we refer to the complex number in polar form as given by this. And remember, r here is just the modulus of the complex number, so you'll often see it written like this. So the polar form of a complex number is when it's written in this form, r e to the I theta. And this is where r is the modulus of the complex number, and theta is equal to something called the arg of z, which is the word argument. So it's called the argument of the complex number. And this is the modulus of the complex number. Turns out that we can calculate both of those by knowing a and b, because if you want to calculate theta, if you look here, the tangent of theta is b over a. So theta turns out to be the arctangent of b divided by a. That's the argument of the complex number. And we've already shown how to get the modulus. So given any number in rectangular, any complex number in rectangular form, you can convert to polar form by use of this formula and by use of the fact that the modulus is the square root of a squared plus b squared. So given any number in complex form, we can transform it, given any number in rectangular form, we can transform it into polar form. But I feel like I need to do some convincing here, so I'm going to convince you that Euler's formula is in fact true. So just to state it again, Euler's formula is this formula here. One of the most important things you learn in this course is how to use this formula and manipulate it. We're going to be doing a lot of that over the next couple of weeks. A is the real part, B is the imaginary part. We've talked about what the argument and the modulus are. Why is this valid? So if somebody is going to tell you mathematically that a quantity is an exponential, if I'm going to make the case that cosine theta plus I sine theta behaves like an exponential, then it means three different things. And I'm going to go over each of those three things with you, starting with exponential law. If this quantity is going to behave like an exponential, then it needs to satisfy this exponential law. So for example, if I had e to the I theta 1 times e to the I theta 2, we want to show that that's equal to e to the I theta 1 plus theta 2. In other words, you can add the exponents. That's one of the biggest properties that exponentials have. So based on Euler's formula, this would be cosine theta 1 plus I sine theta 1 times cosine theta 2 plus I sine of theta 2. And if you were to multiply these out, you'd get cosine theta 1 cosine theta 2 plus the other term, excuse me, this would be minus. The other term without an I is the last part, because you get I times I, which is I squared, which is negative 1, would be sine theta 1 sine theta 2. So that's the real part. Now what are all the terms that are multiplied by i's? Well, if you look, you've got a sine theta 1 cosine theta 2 from here. And then you've got the outermost terms, which would be cosine theta 1 sine theta 2. Okay, well, this is where you dig into your pre-calculus textbook and you say, I vaguely recall what these things are. And you are right. This is cosine. This is the addition formula for cosine. Plus I times, and then this piece here is the addition formula for sine. But this is cosine of an angle plus I times sine of an angle. So by definition, this is e to the I of that angle. And so the first check mark is in the book. This Euler's formula, which I can't show you once again that these are equal. I can't prove that to you mathematically, but I'm defining, if you want to, I'm defining cosine of theta plus I sine theta as e to the I theta, and here's my first piece of evidence. All right. My second piece of evidence that these are in fact related is derivatives have a very special property. If you take the derivative with respect to x of e to the x, you get back e to the x. So we would expect that the derivative with respect to theta of e to the I theta is I e to the I theta, and we're going to prove that. So if I have the derivative with respect to theta of e to the I theta, according to Euler's formula, that's defined as the derivative of cosine theta plus I sine theta. So the derivative of cosine is minus sine. I is just a constant, so the derivative ignores it. The derivative of sine is cosine. And here's the cool thing. Factor out an I from this. If you factor out an I, you're dividing by I. You're going to get cosine theta there. So what do you multiply by I to give you negative 1? In other words, I times this thing equals negative 1, so I times I is negative 1. And you have this, but cosine theta plus I sine theta is the exponential. So we have, once again, proved our second thing. This differentiates like an exponential. So exponential differentiation holds, and I've got one more thing I want to show you to convince you that Euler's formula is true. We're going to look at Taylor series real quick. We know that e to the x has the Taylor series 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, and so on. You would have learned that. That's called its Maclaurin series. You would have learned that in Cal 2. So if that is the Taylor representation for e to the x, then the Taylor representation for e to the I theta would be 1 plus I theta plus I theta squared divided by 2 factorial plus I theta cubed divided by 3 factorial. I'm going to go out a couple more terms here. And so on. So what I want you to observe here is something that happens. I squared is -1, so this term is negative theta squared over 2 factorial. This one, I cubed, is, do we recall at all what I cubed is, going back up to the very, very top? Right, I cubed is -I. So I cubed is -I, so this will be negative I theta cubed over 3 factorial. I to the 4th is 1. I to the 5th is the same thing as I, because if you subtract 4 from the exponent, it stays the same value. I to the 6th would be the same thing as I squared. I squared is -1. So this would be negative theta to the 6th over 6 factorial. I to the 7th is the same thing as I cubed. I cubed is -I. And so on. The pattern continues. But what's really interesting here is take all the real terms. Take all the terms without i's. You've got 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial. You can see the pattern here. The next term would be theta to the 8th over 8 factorial, and so on, right? Now take all the terms that have i's, this term, this term, this term, and so on. Factor out the I, and what you have is theta minus theta cubed over 3 factorial, theta to the 5th over 5 factorial, minus theta to the 7th over 7 factorial, and so on. And if you are a really good Cal 2 student and you remember these things, you should recognize them. This is the Taylor series for cosine. This is the Taylor series for sine. So what you end up with is e to the I theta is nothing more than cosine theta plus I sine theta. So there's our third piece of evidence. So from now on, anytime you see e to the I theta, remember in the back of your head that that's really just cosine theta plus I sine theta. In other words, cosine and sine are really just complex exponentials. Cosine is the real part of the complex exponential, and sine is the imaginary part of the complex exponential. So that's how I want you to think about cosine and sine from now on, is they're the real and imaginary parts of this complex exponential. Now, some context is needed here for why we're talking about this. So recall from last class that y of t equal c1 alpha 1 e to the lambda 1 t plus c2 alpha 2 e to the lambda 2 t solves the system with constant coefficients where the characteristic polynomial, which if you recall how to do this is lambda squared minus the trace plus the determinant. This is a quadratic function known as the characteristic equation. By solving this, you come up with lambda, which gives me two eigenvalues. And once you have those eigenvalues, you can solve for alpha 1 and alpha 2, which are the eigenvectors. We did this in Monday's video lecture if you want to go back and look at it. The point is, in all of the problems that we worked on Monday, every time we went to go solve for these eigenvalues, lambda 1 and lambda 2, this characteristic equation gave me real answers. Well, we know if it's a quadratic function that's yielding solutions here, and we're looking for where this function is equal to 0, there are actually three cases. In other words, three things can happen. The first is lambda 1, lambda 2 are both real and distinct, in which case it's just like we did in class on Monday, and you get a linear combination of eigenvector times e to the eigenvalue. Okay, what if lambda 1 and lambda 2 are real, but they're repeated? We know you can get real repeated roots from a quadratic function. Well, in this case, you get c1 alpha 1 e to the lambda 1t, but I can't write down my second solution because lambda 2 is the same as lambda 1, so alpha 2 would be the same as alpha 1, and I would just get a repeat of this. So on Friday, we're going to figure out what that second solution looks like. But today, what we're dealing with is, what if lambda 1 and lambda 2 are complex conjugates of one another? Well, you know, that means lambda 1 is a plus bi, and the conjugate, as we've talked about today, is a minus bi. That's what roots to quadratic functions look like. So our characteristic equation, this would suggest that the solution here is c1 alpha 1 e to the a plus bi t plus c2 alpha 2 e to the a minus bi t. And what you notice is both of these are complex exponentials, just like the Euler's formula stuff we just got through talking about. So the only problem with this is a complex solution to a real valued ODE. We're assuming that when we solve the ODE, A, B, C, and D, they are all real constants, which means it doesn't make any sense for the solution we inherit to be complex valued. And it turns out, with the theorem we're about to look at, you'll never get a complex solution if you don't want one. In other words, I can take this solution and always make it real. Okay? So we're going to use a little bit of Euler's formula that we just learned about, coupled with the theorem that we're about to talk about, to be able to solve this problem when you end up with complex conjugate eigenvalues. So here's the theorem. The theorem states that if you have a complex valued solution just like this one, so if you have a complex valued solution to a linear system where the matrix A is all real entries, which is what we're dealing with, then if you have a complex valued solution of this system, then the real part of the solution and the imaginary part of the solution are real valued functions that are also both solutions to the system. In other words, if you come up with one complex solution, each complex solution generates two real solutions. So this is going to be our idea. We're going to take this guy, we're going to generate a real solution plus an imaginary solution. We're going to generate a complex solution, And then our solution is going to be a linear combination of the real and imaginary parts. And both of these are real. So we're going to determine a complex solution, then pull off the real part and the imaginary part of that complex solution, and a linear combination of those will turn out to be the solution to our linear system. Okay, so I want to prove that that is in fact a true statement. So let's let y be y real plus y imaginary, and I want to substitute in for y in the system above. All right, if you substitute in, you've got the derivative with respect to t of y real plus I times y imaginary equals a, b, c, d times y real plus y imaginary. And it would be helpful here if we just renamed this the coefficient matrix A, like we normally do. Normally our system is written this way. So this is the derivative of y is, so the derivative of y, the derivative distributes. And on the left-hand side, a gets multiplied by each of these. So this is a times the real part plus a times the imaginary part. And here's what I want you to look at. On the left-hand side, you've got a complex function. On the right-hand side, you have a complex function. The only way that these two functions are equal to each other is if their real parts and their imaginary parts are equal. So this implies that the real part, so here's the real part of this function, here's the real part of this function. This implies that the derivative of this is equal to a times this. And the imaginary part, here, the thing multiplied by I on both sides, that also has to be equal. So the derivative of the imaginary part of my solution must equal a times the imaginary part of my solution. But if you kind of squint at this sideways, all this is saying, but this says that the real and imaginary parts of y of t are solutions, in fact, real solutions of the system dy dt equal ay. Because what you can see is if you differentiate this, you get a times it back. Well, that's what a solution to this system has, that property. If you differentiate it, you get a times that thing back. So the real part and the imaginary part of our complex solution do indeed satisfy the original problem. So a couple of examples will make this pretty clear, I think, but the idea is going to be we're going to take and solve for a complex solution. This is the complex solution. And then we're going to simply take the real and imaginary parts, those are both real, and by this theorem, both of those solve the system. We're going to take those and take the linear combination for our general solutions. All right, let's look at two examples. This will get you started looking into the material for this week. I always like to think of this in matrix form, so I'm going to rewrite this as dy dt equal 1, 2, -1, -1, y. So there is our linear system. If we get the characteristic equation, it's lambda squared minus the trace. The trace is the sum of the main diagonal, so 1 plus -1 is 0. And then the determinant is 1 times negative 1. So this is the matrix A. The determinant of A is 1 times negative 1 minus 2 times negative 1. So negative 1 plus 2, or 1. So our characteristic equation is lambda squared plus 1 is equal to 0, which means that lambda is plus or minus the square root of negative 1, and we know that is the number I. So we have two complex eigenvalues, plus and minus I. So rather than take each eigenvalue and figure out each eigenvalue's associated eigenvector, all we need is one eigenvalue according to the previous theorem. If we take one eigenvalue and find the complex solution, I can then take that complex solution that goes along with, say, just I, and break it up into real and imaginary parts to solve the system. And that's what we're going to do. So there's only one case. So the idea is you're going to take lambda equal to I, and you're going to solve for the complex eigenvector alpha that's associated with it. So we know how to do this. You take A minus lambda I, which is subtracting I from the main diagonal. So here's your matrix A over here. I'm going to take and subtract lambda times the main diagonal. So I'm going to subtract lambda from the two diagonal terms. And then we multiply this by a vector a1, a2, and set it equal to 0. If you're unsure where this is coming from, please revisit Monday's lecture. It's the same steps we used Monday. All right, these tend to be a little bit tougher just to see. The real problems, you can just usually see what the value of a1 and a2 are, but it's not as easy here. So what I recommend students take is focus on one row at a time. So just come in here, look at this row, and say, all right, what is that row telling me? That row is telling me that if I take 1 minus I times a1 plus 2 times a2, that result will be 0. Now, because of the way these eigenvalue problems work, you're always going to have one variable that's free. Remember, any constant multiple of an eigenvector is still an eigenvector. That implies that one of these variables is free. So here's what I would do. I would just set, say, a2 equal to 1 here. If you do that, then you're going to have 1 minus I a1 plus 2 equals 0. So a1 would be negative 2 over 1 minus I, right? Now, that's one possible way. I would not recommend that because you're dividing by the imaginary number. So here instead is what I would do. I wouldn't have set a2 equal to 1. I would have set a1 equal to 1. So here, set a1 equal to 1 instead, and what you get is 1 minus I plus 2a2 equals 0. Or 1 minus I divided by negative 2 is a2. Let's just subtract this over, or yeah, that's fine. That's fine. So this is my a2. What is my a1? Well, once you have this, just plug it back in to find your a1. Well, a1 was 1 though, right? So you have your eigenvector, alpha, is a1, a2, which is 1 minus I over negative 2. And I would clean this up a little bit because you want this to be as neat as possible before you do the next step. Remember, I can multiply the eigenvector by any scalar, and it still is an eigenvector. So if I multiply this eigenvector through by negative 2, you see we get something nice like that. So this is my complex associated eigenvector. What this means is that my solution to this problem, my complex solution to this problem, and I'll call it y sub c for complex, is alpha e to the lambda t, which is negative 2, 1 minus I, e to the lambda here was I, so e to the I t. Okay, but that is a complex solution. We need to separate, by the previous theorem, we need to separate this into its real and imaginary parts, which we're going to do below. So you've got the complex solution. Let me encourage you to split this vector into its real and imaginary parts. If you look, this vector is -2 plus 0i in the first component, 1 minus I in the second component. So another way to write that is -2, 1 plus I times 0, -1. So you see that? You've got -2 and 1 is the real component of that vector. And then the things that are multiplied by i's are 0, -1. That's the imaginary component of that vector. And so that is multiplied by e to the it. But we know from today's lecture that e to the it is cosine t plus I sine t by Euler's formula. So now all I need to finish out this problem is I need the real part of this solution and I need the imaginary part of this solution. So the real part is, this is an a plus I times b, this is an a plus I times b. Foil this out and collect all of the terms that don't have i's. So try to do this without actually foiling everything out and stringing it apart. So look at the first term. You've got -2, 1 times cosine t. That will not have an I. So you've got -2, 1 cosine t. And then if you look at the imaginary term times each other, I times I is -1. So this term times this term will actually be real. It'll actually not have an I as part of it. So minus 0, -1 sine t. Now if you look at the imaginary parts, these are the parts that are multiplied by the I. So this term times this will have an I. So this is the imaginary term. Notice I don't include the I, right? The imaginary part is the thing that's multiplied by the I, not the I itself. So this is multiplied by an I in this expression. And then the other part, which is multiplied by an I, is the first term times the last term here. So you've got the -2, 1 times sine t, that'll be multiplied by an I. So there's my real part and my imaginary part, and by the previous theorem, then my solution y of t is simply a linear combination of that real part and the imaginary part. So what does my general solution end up looking like? I think for most people the best way to write this is in kind of this row vector form. So scan across the very top and let's write down the first component. So this is, write it this way. So looking just at the real part, along the top component is -2 cosine t. So -2 cosine t. The bottom part is cosine t plus sine t. So cosine t plus sine t. Right? So there is the real vector. Now how about the imaginary part of this vector? The imaginary part, the top is just -2 sine t. And the bottom term is negative cosine plus sine. So negative cosine plus sine. So that's one way to write it. This is kind of the vector form. But I actually find for most people it's better to write it in terms of the x and y coordinates. So the x coordinate and y coordinate. The x coordinate is the top component, which is -2c1 cosine, minus 2c2 sine. And then the y coordinate is, if you look across the bottom here, is c1 cosine plus c1 sine minus c2 cosine plus c2 sine. So this is my preferred way to give the solution to these complex problems, is to write down the components, right? This is the vector form of the solution. This is the component form of the solution. So I think for most students, writing down what the x coordinate is doing, writing down what the y coordinate is doing, I think that is the thing that you should probably do. All right, let's do one more. What you'll notice on this one is the eigenvalue I was sort of simple. So we're going to look at one more example where the eigenvalue is not quite as simple here. All right, so write this in the form, matrix form, dy dt, -1, -2, 2, -3. So that our characteristic equation is lambda squared minus the trace. The trace of A is the sum of the main diagonals. So it's the opposite of the trace. It's the opposite of the trace that goes here. And then plus the determinant. So the determinant of this is the main diagonals multiplied together minus the off diagonals multiplied together. So that looks like 7. Let me just double check. This is the easiest place to make a mistake on these problems. So let's see, -1 times -3 is +3, minus a -4 is +4, 7. Yeah, it looks good. So lambda squared plus 4 lambda plus 7. You notice right away it doesn't factor, so let's throw it into the quadratic formula. So this is -2 plus or minus. So let's see, 16 minus 28, that would be the square root of -12, but the square root of -12 is the square root of -4 times 3, which is 2 square root -3, which is 2 times square root 3i. Yes. So 2 square root 3i, but I'm dividing this by 2, right? So this is -2 plus or minus square root of 3i. Just double check. Looks good. Okay, so these are my eigenvalues. Remember, I only need one of them. So I'm going to take one of them and subtract each term of this by those. So we've got, to find our eigenvalues, I'm going to take -1 minus -2 plus square root 3i. And then -3 minus -2 plus square root 3i. And let's see, this simplifies to -1 plus 2 is 1 minus square root 3i. And then this is -3 plus 2 is -1 minus square root 3i. Okay, so I need to solve that equal to 0 for some non-trivial solutions. This is where using that technique I showed you before pays off. You know, you're just going to take and solve 1 minus square root of 3i times a1 minus 2a2 equals 0. I just looked at the top row here. So this times a1 plus -2 times a2 has to equal 0 according to this multiplication here. So I need to solve this, and just like previously, I'm going to set a1 to be 1. So if I do that, And I've got 1 minus root 3i. Minus 2a2 is 0. So I've got 1 minus root 3i divided by 2 is a2. So I know that my complex eigenvector is 1 over this, and I should probably multiply the top and bottom by 2 just to make it a little bit nicer. So there's my complex eigenvector, which means that my complex solution is alpha e to the lambda t, which is this complex eigenvector times e to the lambda, and lambda here is, remember I used the positive one, so I only needed to use one of these, and I used the positive one. So this is negative 2 plus square root of 3i times t. All right, so you still want to do everything the same way we just got through doing. You want to write this, here's the real part of this vector, the imaginary part of the vector is given by that. And then you want to separate out this next piece. This next piece is e to the minus 2t times e to the square root 3it. Right? Because you've got, we didn't have a real part to our eigenvalue last time. That's the main difference here. Okay, so one more little step. We can use Euler's formula. Remember, e to the I theta is cosine theta plus I sine theta. And so here, theta is square root of 3t, right? So this would be cosine square root 3t plus I sine square root 3t. Okay, now it's in a form where I can FOIL it real easily. I can tell you, okay, here's the real part. The real part is, well, all of these are going to be multiplied by e to the negative 2t, right? So you might as well just put that out in front of both the real and imaginary parts. It's going to be part of both. Okay, so let's ignore that term for a second because it's going to be on all of them, and let's look for the real part. So it would be 2, 1 cosine root 3t. And then it would be minus, because of the I squared, I times I gives you negative 1, 0 negative root 3 sine root 3t. And then the imaginary solution would be, let's see, you're going to get 0 negative root 3 times cosine. And the other term, 2, 1 times this, is the imaginary part. So then finally my solution to this problem is C1 times the real part plus C2 times the imaginary part. And we're going to talk about what this looks like in the phase plane. We're going to talk about what this looks like in the phase plane after you've had a chance to do this week's Maple quiz. I kind of want you to see some of these things yourself, and then we'll talk more about this Monday and Wednesday of next week. Okay? But this is the solution. We could write it in component form. So if you scan across the top component, that's the x value. If you scan across the bottom component, that's the y value. So we can start with x and y. So the top component is 2e to the negative 2 cosine root 3t plus 2e to the negative 2 sine root 3t. That's x. And then y would be, the bottom component would be e to the negative 2t cosine root 3 Oh, I'm forgetting my C1s and my C2s, sorry. This would be C1 times this piece, C2 times this piece. Here it would be C1 times this piece, plus C2 times that bottom piece. You see how these can get quite messy. And so that would be the solution in this case. So this is the y of t component. You can see this if you were to solve these in Maple, and that's what I want to bring your attention to real quick, is getting used to looking at these solutions in Maple and then sort of associating what their phase portraits look like. Here, because of this exponential e to the negative 2t on both terms, over time, all of this will head in towards 0. Both the x-coordinate and the y-coordinate will decay to 0. And because you have cosine and sine, you get this sort of rotation that occurs. So you get a spiraling in towards 0 behavior over time, which is why we would call phase portraits of this type something called a spiral sink. Like I said, we'll talk more about that in the lectures ahead, but I do want you to know where you should be looking this week for your Maple work. So let me go quickly here, bring up Maple. The file that I want you to be aware of is this file called Examples of Linear 2x2 Systems, or Sketching 2x2 Systems. You'll notice that I go through and show you for different system matrices, you know, getting the characteristic polynomial, the eigenvalues, how to solve the system. So you notice I have the system set up over here, how to obtain solutions. Notice Maple gives it to you in component form with x and then y. And then I've showed you how to do this. Don't use the phase portrait command, by the way. I probably should have updated this. It's an old command. It probably still works, but just use DE-plot. So if you use DE-plot, you get the same result. You have to load DE-tools. Yeah, you have to load DE-tools to do this, but just use DE-plot instead of phase portrait. But here is the phase portrait for this one. This system had 2 real eigenvalues. And so this is the behavior that we would expect to see with 2 real eigenvalues. And then this one had 2 negative eigenvalues, and so on. And I go through in detail all the different types that you can run across, all the different behaviors that you can run across. So this would be a really good one to reference for Maple Quiz 6, which you're currently working on. I just wanted to show you real quick. The problem that we just got through doing looked an awful lot like this one. We had -2 plus square root 3i, -2 minus square root 3i. This one's kind of similar. And you look what I was talking about, that spiraling behavior where over time all the solutions spiral in toward the origin. You can see here this looks a lot like the problem we just did in our notes, where you've got the e to the minus 2t, which spirals everything in. So this is a brief introduction to the complex problem today. I realize you are probably in need of more examples. That's why I have extra videos out there, and I do encourage you to work on some of the practice problems out of the textbook that I've linked for Quiz 6 as you're getting started. All right, I'll be back dealing with the third and final case on Friday, the repeated root case. I hope everybody's doing well, and if you have any need of me, get in touch with me via email or stop by office hours between now and then. Have a good day.